Hello, welcome, and thank you for coming to my talk on gravitational wave Bayesian inference. So just as a little bit of background, my name is Charlie Hoy. I am the Dennis Sharma Research Fellow at the University of Portsmouth in the UK. And I've been doing gravitational wave data analysis now for almost a decade. And I'm a part of the LIGO-Virgo-Cagra collaboration and also the LISA consortium. And during that decade, I've pretty much just been doing gravitational wave Bayesian inference. So it's my privilege to talk to you today about what I've been doing for the last 10 years, really. So firstly, what is gravitational wave Bayesian inference? What is the problem we're trying to solve? Well, it all comes down to this. What we're trying to do is go from the left-hand side, which is an image of the gravitational wave strain data, and we're trying to go from that on the left-hand side to try and infer something about the system that produced that gravitational wave that we've seen in the data. So what you're seeing on the left-hand side is actually the gravitational wave strain data for the first gravitational wave detection, GW5914, in the LIGO Livingston detector. And when we perform this gravitational wave Bayesian inference, if we assume that it was produced by two black holes that coalesced and merged, we can infer using this technique that the two black holes that merged likely had masses around 35 and 31 times the mass of our sun. And that's what's shown on the right-hand side here, but don't worry, we'll go into details about what that plot means and how to read it later on in this talk. So why do we care about gravitational wave Bayesian inference? Well, it allows us to do lots of really cool astrophysics. For example, it allows us to obtain an independent measurement of the Hubble constant. It allows us to test general relativity and actually allows us to understand the mass and spin distribution of black holes. So it allows us to say, are black holes 100 times the mass of our sun as likely as black holes 10 times the mass of our sun, for example? And it can be used to sort of infer how binary black holes form in the first place as well. We can also use it to constrain the neutron star equation of state, which is very exciting, as that is currently an unknown in our field at the moment. So firstly, what I wanted to do was start off with an analogy of what gravitational wave Bayesian inference is. So what you can see here is an image of the river that runs through Toulouse. And what I want you to imagine is that you're on the side of this river. You're on the riverbank and you're wearing a partial blindfold. So all you can see is the ripples of water on the edge of that river, and you can't see anything else. So essentially, this is your view. Everything is dark except for the very edge of that riverbank. And I want you to imagine that I've just dropped a rock somewhere in the river, and I want you to infer where I dropped that rock. Well, one way you could do that is you could stand where you are on the riverbank and wait to see a ripple, okay? And the ripple might look something like this. And just a few meters down from where you're standing, there could be another ripple. And a few meters again, you would see another ripple. And what you could do based on how long it's taken from where you're hearing the rock hit the water to how soon you see those ripples at those three distinct spots, you can draw circles as to where that source may have come from, and where they all overlap is going to be where I dropped the rock in the first place. So just like that, you've been able to infer where I dropped the rock, okay? And we can actually go one step further. We can actually try and infer what the shape of the rock is that I dropped in the first place. One way you could do this is you could find lots of rocks on the side of the riverbank, and you could repeat the experiment and just drop the rocks in that exact point of the river where you just inferred I dropped it, and look at what the ripples look like at each of those points. So you can see here on the bottom left-hand side is an example of a rock and the waveform that you may have seen. And on the right-hand side, you can see another rock in a different waveform. And you can see just by looking and comparing those ripples to what I saw originally and what I'm seeing now in my experiment, you can see that it's unlikely the one on the right, because it looks completely different. So just like that, again, you've been able to infer what the rock is that I dropped in the first place. And you've been able to perform Bayesian inference in essence. And this is exactly pretty much what we do in gravitational wave astronomy. We look at our strain data and we generate lots and lots of different gravitational waveforms. We compare it to the data. So here in the gray, you can see that gravitational wave strain data for the first gravitational wave detection that I showed you earlier. And on top is a random gravitational wave signal that I've generated from two binary black holes coalescing with different parameters. And if I flick back and forth, you can see, if I flick back and forth, you can see that that white curve doesn't look like the gray underneath. You can see that there's some more oscillations in the high frequency end that are not there in the data. So it's unlikely it was produced by that gravitational wave. I can generate another gravitational wave, just like generating or throwing in another rock. And I can see here that again, now I've got a different wavelength to what I see in the original data. So again, it doesn't look like the data underneath. So it's unlikely to be formed by that gravitational wave signal. And lo and behold, if I find the exact gravitational wave signal that matches the data underneath, just like this one here, I get a very high probability that it was caused by that one. And this is actually the maximum likelihood gravitational wave signal for the first gravitational wave detection, which is why it looks very similar to the data underneath. And you can see that if I go back and forth, it again looks exactly like the data. Sorry. Yes. So you can see that it's got the wavelength right and the amplitude as well. So how do you actually perform gravitational wave Bayesian inference? Well, it all comes down to pretty much a single equation, and that's what's known as Bayes' theorem. So this is what's shown here, and it looks a little bit intimidating at the start, but it's just a series of probabilities, and we'll go through each one by one. So the posterior on the left is what we're trying to calculate. The posterior is the probability of the system that produced the observed data having parameters lambda given the data that I've observed and my model M. Okay, so going back to the rock analogy, this could be, for example, the radius of the rock, the mass of the rock, and also where I dropped it in the riverbank. And this is what I want to know. I want to know what is the probability of that rock having radius 100 centimeters and weight 0.2 kilograms. What is the probability of that given the data that I've just seen in the on the side of the riverbank? And on the right-hand side, there are multiple probabilities. We'll go through them one by one. The prior is my prior belief on what I think those parameters are. Okay, so if we go back to the rock analogy, what you could do is you could look on the side of all of the rocks on the edge of the riverbank and say, okay, I'm likely to see a rock that looks like this, but I'm unlikely to see a rock that's, for example, granite, very heavy, huge mass. I'm unlikely to see that because it's not on the side of the river that runs through Toulouse. On more of an astrophysical point of view, if we consider black holes, we can choose multiple priors, and the prior can be anything you want it to be. So for example, we can assume that all black hole masses are equally likely, as shown here by the orange curve. We could say that a black hole of mass 100 is as likely as a black hole of mass 2. An alternative would be to use sort of like an astrophysical understanding and say we know from stellar evolution that stars follow the Salpeter IMF, and therefore are more likely to have lower mass and higher mass. So you may think that black holes would follow a similar relation, and therefore we're more likely to see lower mass black holes and higher mass black holes, and that's what's shown by the gray line in this plot here. So the prior is anything you want it to be, which is why you've got to be very specific and state what your priors are for any problem that you solve. So just as an example for the gravitational wave problem, if there is no preferred sky direction, then what we would assume is that we're completely uniform in the sky. It could have come from anywhere. We don't know where it's come from. So let's just take all sky positions as equally likely. Now, we do know that black holes have a maximum spin, assuming the Kerr metric. So the spin magnitudes have to be less than 1. But otherwise, let's say they're all equally likely. We don't know what the spins are a priori. Could be equally likely to be 0.2 or 0.8. And if we have no information of the mass distribution, then we can assume a uniform distribution of masses and say that black holes of mass 100 are as equally likely as a black hole of mass 10, because we don't have any other information to combat that. These are all choices that you are free to choose. It could be anything you want it to be. Now, the next term is a likelihood. Okay? The likelihood tells us the probability of generating the data given those specific set of binary parameters lambda and my model M. And we'll go through these one by one as to what all this means. So in Tito's lecture yesterday, you're introduced to the Whittle likelihood or the Gaussian likelihood, and that's what's shown here. So we have the probability of the data given our binary parameters lambda and model m is equal to the exponential of -1/2 multiplied by the noise weighted inner product of the data minus the model with itself. Okay, I won't go into details as to what the noise weighted inner product is because Tito covered that in yesterday's lecture, but I will go through and remind you of what the data is and what the model is, because that's very important for gravitational wave Bayesian inference. So when it comes to the data, we know that the data, if we assume there is a signal hidden within there, the data is comprised of a signal, H, that's our real gravitational wave signal that we're trying to infer the properties of, and it has some noise as well. That is just noise in our gravitational wave detectors. And we're trying to extract or understand the properties of that signal that's hidden within that data. And this can be defined in either the time or the frequency domain, which was covered in Quentin's talk as well from a few days ago. And the challenge here is that our gravitational wave signal H has a much lower amplitude than our gravitational wave noise. So we're really trying to extract a needle in a haystack here and trying to extract the properties from something that has a very small amplitude. So if we look at the noise, again, this is just a recap of Quentin's talk from a couple of days ago. We know that the noise can be described by the power spectral density, and that's what's shown here on the right-hand side. We have the frequency on the x-axis and the strain noise on the y-axis. And what you can see here, this tells us essentially how sensitive our detectors are. So in the gray line, we have a PSD that's been generated based on 32 seconds of data. And in the gray dashed line, you can see the PSD that's been generated over 2,048 seconds of data. Again, I won't go into any details about this because this was covered in Quentin's talk from a few days ago. But a key thing that I'd like you to take away from this is that the more data we have, the better when generating a Welch PSD, which is what's shown here. So you can see that when we analyze 2,048 seconds of data, the PSD is a lot smoother and has less noise associated with it. Yeah. Now, the next most important thing in the likelihood is our model and our signal. So if we're in a regime where we could generate the real gravitational wave signal, we could solve Einstein's equations and we could generate the gravitational wave signal that we would expect for every single binary configuration, that would be amazing because we wouldn't need a model. We would just generate and solve numerical relativity for every single point in the parameter space and compare it with what we've seen in the data. This is essentially taking every single rock in that analogy, dropping it in the water and comparing it one by one. Now, unfortunately, we're not in a regime to do this because analytically solving or numerically solving Einstein's equation is actually very challenging and very time consuming. So what we have to do is generate a model to model the gravitational waves, give an approximate gravitational wave signal that would have been produced by the binary parameters lambda. Okay, so I want to be able to give this model any set of binary parameters, for example, black holes of mass 50 and 10, spins 0.5 and 0.2 on the individual components, and I want to get back what the gravitational wave would look like for that system very quickly. And we're in a regime at the moment, and we're in a very lucky and privileged position where we have lots of different gravitational wave models that we can use. Okay, 3 of them are shown here. So we have the NR surrogate on the bottom left, IMR phenom XPNR in the middle, and SEOBNR V5 PHM on the bottom right-hand side. And these are the leading state-of-the-art models from 3 different waveform families. From the surrogate on the left, the phenomenological in the middle, and the effective one-body on the right. Now, one thing I want you to take away from this is that even though these models approximately generate the gravitational wave signal, they will have different underlying assumptions within them. And what that means is that if I give each of these models the exact same set of binary parameters, I will get back slight differences in the gravitational wave that has been produced, okay? And that's what's shown here. This is for a very extreme system, mass ratio 4:1, very, very high spins at an inclination angle that gives very high degree of precession and higher order multiple moments. And what you can see here is that when I generate these 3 gravitational wave models, they do disagree with one another. And this is a phenomenon known as waveform systematics. And what this means is that when you analyze your gravitational wave signal, you perform this gravitational wave Bayesian inference with the different models, you will get back slightly different parameter estimates as a result of the different underlying assumptions in each of the models. I won't go into details about that now because I don't have a huge amount of time, but if you're interested, you're more than welcome to ask me about waveform systematics. Okay, so that comes back to the Gaussian likelihood. So we've explained what the data is, and we've explained what our model is. So when we look at this equation, what we're essentially doing is subtracting our model from the data. We're trying to minimize the residual. Our data is comprised of h plus n. So if we're in the perfect regime, where our model is a perfect description of general relativity, and we perfectly found the set of parameters lambda, then if I subtract that from the data, I'm just left with noise at the end. And that's perfect. However, in reality, that's not going to be the case. I don't know the parameters exactly. I don't know the parameters lambda that generated that gravitational wave in this first place, and my model is not a perfect description of general relativity. So what I'm trying to do here in this equation is minimize the residual, trying to minimize the difference between the noise and any extra terms left in the data. Try and subtract off as much as I can of that gravitational wave signal h that's in the data. Okay, and then the last term in Bayes' theorem is the evidence. Okay, and the evidence is essentially a normalization constant. It is the probability of the data given my model M. Now, unfortunately, generating the evidence is actually a very difficult thing to do. And the reason for that is because if we're considering a simple quasi-circular binary black hole system, then if I want to generate the evidence, what I have to do is perform a 15-dimensional integral over a huge region of the parameter space. So this is actually a very difficult problem to solve. There are techniques to do it, but it is a very difficult problem. However, if you can generate and get an estimate for the Bayesian evidence, then you can do what's known as hypothesis testing. You can compare different hypotheses in a Bayesian standpoint, and the way to do that is you just look at the ratio of evidences. So here, this is what's known as a Bayes factor. This is the Bayesian equivalent of a hypothesis test, essentially. And what you're doing here is you're comparing the evidence that there's a signal in the data versus just noise. So if I look at that ratio, I get a Bayes factor for the signal to noise. And if that number is really, really big, then I think I have a high probability that there is a signal in the data there. And in general, if you analyze any gravitational wave data with a gravitational wave, this number is going to be huge. So if you can get a good estimate for the evidence, you can do all of this fun stuff about hypothesis testing as well. You can also use this to test the hypothesis of different models and see which model better fits the data as well. So again, if you're interested in that, you can ask me later. Okay, so now we get on to the difficult bit. How do we actually calculate the posterior distribution? Well, one way we could do this is we could just grid up the space and calculate the likelihood times prior at every single point in the space. If I do that and I sum them all together, I've got an evidence. I've got an estimate for the evidence, and I know where the region of highest probability is because I've calculated it everywhere. Now, in one dimension, this is fine. I can do this. I can take 100 points on this one-dimensional line in the bottom right, and I can calculate the likelihood times prior everywhere, sum them all together, and evaluate Bayes' theorem analytically. Okay. In 2 dimensions, again, it's doable, depending on how big the space is. 3-dimension, 4-dimension, it gets higher and it exponentially grows in computation. So if, for example, I take 4 unique points in each dimension and I have 15-dimensional parameter space, I'm going to be evaluating this equation more than 1 billion times. So this isn't feasible. So what we tend to do is we do something what's known as stochastic sampling. Okay, so stochastic sampling is a technique that does not evaluate the likelihood times prior at every single point in the space. What it does, it randomly walks around the parameter space to try and find the region of highest probability. Okay, and that's what's shown on the right-hand side here. So you can see I'm randomly generating new points and moving around the space. What you can see, if you can see my cursor, it's picked up this region here as the highest probability region in this 2D space. Okay, but you might be asking yourself, how do I get an evidence? How do I get an estimate for the evidence? Because now I'm not calculating the likelihood times prior at every single point in the space. I'm randomly walking around it. Well, there are some very clever techniques out there for bypassing this. For example, Markov chain Monte Carlo. What this does is it takes, it calculates the likelihood times prior at each point that you're at currently, and then it looks at a new point, a new proposal point. And what it does, instead of trying to work out what the evidence is, just divides the two. We know that the evidence is a constant, it's a normalization constant. So if I calculate the likelihood times prior at one point and calculate the likelihood times prior at another point and divide them, I've wiped out my evidence term. And now I can look at where the highest likelihood region is and keep jumping to those higher likelihood or higher probability regions. Now I want to take you on another analogy here. So this is an image of a mountain range in the Alps. Okay, and what you can essentially think of is that this mountain range is your posterior distribution, and you want to walk around this and try and map out what this mountain range looks like. Try and draw samples from this mountain range, from this posterior distribution. So if you just take, so if you just take that current point and keep jumping to higher probability regions, then what you'll do is you'll end up getting to the maximum there, which is shown here. You can get there in, let's say, 1, 2, 3, 4, 5, 6, 7, 8 steps, and you can get to the highest probability region. But you haven't mapped out that mountain range at all. You've jumped to what's known as the maximum likelihood. And there's also a possibility that if you're wearing that partial blindfold from earlier and you did the same technique, there's a possibility that you could get stuck at a local maxima. So you could walk up this mountain range and you could think that you're now at the maximum at that secondary peak, because everywhere you walk around, you're going downhill. Now, in reality, if you were to take that blindfold off, you know that you're no longer at the peak and you're stuck at a local maxima. So how do you get around this? Well, one way to do this is to sometimes accept going downhill in order to fully explore the space. And that's what's shown here. This will take a lot longer. You're going to walk around the space in what you might think is an inefficient way. But if you go backwards every now and then and accept points that go downhill, you can effectively map out that entire mountain range. And you can walk around and understand where the highs are, where the troughs are, and you can explore, for example, here, you can explore that local maxima as well as a global maxima. So that's what brings us on to Markov, the Metropolis-Hastings algorithm. So what this technique says is it says, okay, I'm going to draw a random starting point for my parameter space lambda. And then just like before, I'm going to pick or propose a new point lambda prime. Okay? Now, instead of just accepting that straight away, what I'm going to do is I'm going to calculate this acceptance probability. So this acceptance probability is defined here. It is the minimum between 1 and the product of the likelihood times prior at my current point and the new point. And if that acceptance ratio is greater than a random number between 0 and 1, I'm going to jump to that point. Otherwise, I'm going to choose another point. So if I always propose a point that is higher likelihood than where I am, I'm going to always accept that point. But sometimes I accept walking downhill in order to fully explore the space. And that's what's known as the Metropolis-Hastings algorithm. And just like what I showed you previously, that allows you to fully explore that mountain range and walk up and down, trying to map out that full surface. Now, another technique to draw samples from the posterior distribution is known as nested sampling. This is a slightly different algorithm. And the way this works is you take your parameter space, what's shown here is a two-dimensional space. Doesn't matter what the x-axis and y-axis are, it's just a region of the space. And what I'm going to do is I'm going to randomly sprinkle a series of points in this space, which is shown by these white dots. Okay, so I've just randomly thrown those in the space. And then what I'm going to do is I'm going to calculate the likelihood times prior at every single one of those points. Okay, I'm going to find the point that has the lowest likelihood times prior, which is this point here that's now gone gray, and I'm going to move it to a higher likelihood point. So I'm going to draw a sample from the likelihood constrained prior that's now of higher likelihood than where I was initially. And I'm going to do this over and over again. And what you'll see is that those points, those live points, will start to converge to a higher probability region. Okay? And what's wonderful about nested sampling is it was actually solved to generate or to get an estimate for the Bayesian evidence. Because what I'm doing is I'm throwing points around the whole space and evolving them to the highest probability regions. I'm walking and exploring the full space. Now, you actually get back posterior samples. You get back an estimate for that mountain range as a byproduct, because what I can do is then calculate a series of weights associated with how likely they are compared to the maximum likelihood of where I think I am. So the maximum likelihood to be somewhere in this white dot. And I can calculate a series of weights and then draw samples based on those weights and all of the dead points that I have seemingly thrown away when trying to converge to the maximum likelihood spot. So nested sampling is an extremely powerful technique to try and draw samples from that posterior or to map out that posterior surface. And like I said, the beauty of nested sampling is you get back a really nice estimate of the Bayesian evidence as well, which can be used for this hypothesis testing. So how do we actually do this in practice? Well, what we do is we use a code known as Bilby. Bilby is the Bayesian Inference library. And what this does is it interfaces with lots of stochastic sampling techniques out there and will solve both gravitational wave and non-gravitational wave Bayesian inference problems. Okay, so what it does is it interacts with MC, dynasty, Bilby MC, multi-nest, lots and lots of different sampling algorithms, and will allow you to fully explore that mountain range that I showed you earlier and map out that mountain range over as many dimensions as you want. Now, what's actually output by Bilby is this, a big table, a big spreadsheet. And what you see are individual samples from that posterior distribution. So essentially, these are points that you found when walking around that mountain range. Each point will be that you, after the reweighting procedure, each point will be some point within your posterior. And what you can see here is that each column represents different parameters of your model. So here you can see on the left-hand side, we've got right ascension, declination, so where it came from in the sky. You've got the primary source mass, secondary source mass, and the luminosity distance. Now, in reality, this table is quite big in terms of the number of parameters, because if your model takes in 15 parameters, let's say mass 1, mass 2, different spin degrees of freedom, what you can actually do is you can generate another 40, 50 parameters based on those. So what you're probably looking at is a spreadsheet or a table that has 70-ish columns for all of the different parameter configurations that you can have. For example, you can have the mass in the detector frame versus the source frame by just allowing for the expansion rate of the universe. Okay. Now, this data that is output by Bilby is stored in a JSON or HDF5 file, and it can be extracted using various Pythonic routines, for example, NumPy, H5Py, Pandas, psummary, etc. Now, what you can do when you're looking at this spreadsheet, because it's quite hard to understand and draw correlations from just a big table, what you can do is you can look at each column individually. And you can take all of those columns and histogram them. So look at how many samples are within each bin within your histogram, count them all up, and make sure that your probability under the curve is equal to 1, so you get a probability density. And what you can do is you'll get back a figure that looks something like this. So this is the primary source mass that we inferred for GW 150914, the first gravitational wave detection. And what you can see here is that where your histogram peaks, so that will be up here, which has the highest probability density. That is your median, where it's most likely to be from your median estimate. And you can also look at how wide or how wide your histogram is by looking at how much probability encapsulates 90%. So that's what's shown here by these vertical dash lines. So within that region, it encapsulates 90% probability. And if you wanted to, you can put a stricter constraint and look at only the 50% credible interval if you wanted to. And that would be inside this region. And what you can see on the top is you can see the median with a plus minus, so an error associated with that. And that is your 90% credible interval there. And if you're interested, you can make this plot with psummary or matplotlib. You can ask me if you're interested. Now, what you can also do, instead of just looking at a single column, you can look at multiple columns. So now let's say we want to look at mass 1 source, mass 2 source, and the luminosity distance. We want to compare all of these 3 columns and try and draw connections between them. What we can do is we can generate what's known as a corner plot. Okay? Oh. Yes, we can generate what's known as a corner plot. So what you're seeing here is essentially correlations across the parameter space. You can see along the leading diagonal are those same 1D histograms for each of those individual columns in your spreadsheet. And in the 2D panels, you can see the correlations between the two. So if we focus here on, for example, mass 1, mass 2, what you're seeing here by the different lines or different contours are the different probability regions. So these are all configurable, but by default, the one on the outside is going to be 3 sigma. So 99.7% of the probability is going to be encapsulated within that region. The second innermost one, so here, this is going to be 2 sigma, so 95% probability is going to be within that region. And finally, the third region here is 1 sigma. So 68% of your probability lies within that region. And this is really powerful by looking at the corner plot, because you can see degeneracies or correlations across the space. So what you can see here is that within your 1 sigma uncertainty, my primary mass could be around 36 and correlated with around 30 in my secondary mass, or it could be 32 and 32. Okay, so you can really see those correlations across the parameter space and see how my, for example, primary mass is related to the secondary mass across that spreadsheet, across that big table. And you can do this over as many dimensions as you want. The difficulty is that it just increases computation to this more and more dimensions, but it is completely possible. And if you'd like to make this plot, again, you can do it with psummary or corner.py, and you can ask me how to do that if you're interested. Now, something else you can do is you can look at, exactly like I did in that first analogy, by figuring out where I dropped it in the riverbed, you can also try and work out and get an estimate for where that gravitational wave occurred in the sky. So what you can do is take the 2 columns for right ascension and declination, and you can produce what's known as a sky map. And you can again look at that 90% credible interval and 50% credible interval down here on the bottom right-hand side of this figure. And you can actually estimate roughly how many square degrees that probability encapsulates. So this is again for the first gravitational wave detection, GW 5914. And you can see in the bottom right that the 90% confidence interval is around the sort of -60 and around 12 hours to 6 hours sort of region. And you can calculate that 90% area encapsulates 200 square degrees. And if you reduce that down to the 50% confidence interval, so how much probability is encapsulated within the 50% credible interval, you get that down to 61 square degrees. So it's more likely to be within the 61 square degree estimate, but it could be pretty much anywhere within sort of 200 square degrees. And again, if you're interested, you can make a spot with psummary or LIGO.SkyMap. One thing to bear in mind here is that I am downsampling my number of posterior samples. So rather than having 100,000 or 50,000 posterior samples, I'm downsampling, just randomly choosing 1,000 rows in my spreadsheet just to reduce the computation a little bit. But this is completely possible and easy to do. So how do you get the gravitational wave samples that have been produced by the LIGO-Virgo-CAGRA collaboration? Well, one way to do that is to use the psummary package. And what you can do is you can import this fetch open samples functionality. And by just passing the name of your favorite gravitational wave candidate, so GW 5914, you can fetch those public samples, and it will have routines to do this. It will fetch it from Zenodo. You can generate all the posterior samples, and just by using this dot plot method, you can generate all of the plots that I've shown you already. You can generate those 1D histograms, those corner plots in the sky map with ease just through this one simple line of Python, essentially. So what this is going to do is it's going to generate that histogram for the mass 1 source, hence the type equals hist. And what it's going to do is just add a little KD on there as well, a kernel density estimate, just for fun. So now we come on to the additional resources. So if you're interested in using Bilby, there is some public documentation online. So you can go to the lsesoft.docs.ligo.org/Bilby. On here is a comprehensive documentation about how to use the code, how it interfaces with the different samplers, and how you can make plots and how you can make those corner plots, histograms, everything like that. And there's also documentation for psummary as well, again, just to read in those sample files and make plots. There is a very good paper by Eric Thrain and Colin Talbot, which I encourage you to read. It tells you all about how to do gravitational wave Bayesian inference and all of the fun complexities associated with it. It also goes into hierarchical inference, which you'll hear about later on this afternoon. And if you have any questions, you're more than welcome to reach out at charlie.hoy@port.ac.uk. Like I said throughout this talk, I'm interested in quite a lot of things about Bayesian inference. So if you're interested, you can ask me about how to reduce the computational cost of Bayesian inference through likelihood acceleration. So one of the challenges with Bayesian inference is the likelihood is actually quite computationally expensive to generate. So there are ways to get around this. For example, heterodyning, for example, multibanding. These are all ways you can reduce the computational cost of the likelihood while getting back statistically identical results at the end. In some cases, you can reduce the cost of your Bayesian inference by 1,000 times by just using these acceleration techniques. I'm also interested in mitigating non-Gaussian noise artifacts. So for example, glitches in the data and how this will impact your data and how it will impact your estimates for the binary parameters. And one thing that I'm particularly interested in at the moment is accounting for model uncertainty in Bayesian analysis. So how can I account for the fact that my gravitational wave models are going to be different in different regions of the space, and how I can incorporate that into my Bayesian analyses. So yeah, feel free to ask me about anything. I helped write P-Summary. I'm the main developer, so if you have any questions about P-Summary, you're more than welcome to ask me. And yeah, that's the end of my talk. So if you have any questions, please let me know. Thank you very much.
Okay. We actually have a lot of time for questions. We have 10 minutes, almost. So feel free to ask any clarification needed, any question. There was a question online by somebody. Okay, the question was, what does the different models tell us about the gravitational wave? And more precisely, this person wants to know after matching the model, what we understand about the observed gravitational wave. Do we understand something about the source of the gravitational wave and where it was created?
A very good question. So what you can do is you can actually compare your gravitational wave model to known analytic solutions of numerical relativity. What you can do, and we've generated numerous numerical relativity simulations, just not at every single point in the parameter space. I think in total, we've got around 4,000, 5,000 numerical relativity simulations for different binary parameters. What you can do is you can generate your model for every single one of those binary parameters and compare it to the known solutions of general relativity. Assuming numerical relativity is a good description of general relativity. You can compare them and you can see which ones are more accurate in different regions of the space. So we know that on average, NR surrogate 7DQ4 is an order of magnitude within its calibration region, an order of magnitude more accurate than the other models. Okay. Now, in terms of our understanding of the binary parameters, well, over most of the space, our models agree very, very well. And up to very, very high SNRs, our models are going to agree very well with one another. It is just when we get up to these sort of really extreme SNRs, around 100 or 1,000, let's say, where we will see these small differences between the models. And it completely depends on where you are in the parameter space. So if we're in the aligned spin limit, where all of the black hole spins are aligned with the orbital angular momentum, our models are going to agree very, very well with one another. If we're in the processing sector, they don't agree as well. But generally speaking, we would prefer the parameters inferred by the NR surrogate 7DQ4 model within the calibration region because it is more accurate, or it more accurately describes general relativity. I think that answered the question.
Okay, thank you. There is another question online. What questions online are flowing now? Probably rocks thrown in the Garonne River, and we have ripples. Question by Philippe Levy-Ramkan. I don't know how to pronounce that. I would like you to elaborate on mitigating non-Gaussian noise artifacts in the data.
This is, again, a very good question. So we know that there are going to be these non-Gaussian noise artifacts in the data. You saw that in the lecture or talk a few days ago. And how can you mitigate this? Well, one way what you can do is you can model that noise transient and subtract it from the data, and then analyze the gravitational wave strain data underneath. This is a technique that's known as what it does is it will simultaneously fit the glitch and the signal at the same time, and it's a way to mitigate the effects. So the easiest way would be to model that glitch, subtract it from the data, and simultaneously fit the astrophysical signal underneath as well. Another way you can do is if your noise is always below, for example, 30 hertz, you can analyze data above 30 hertz in order to mitigate the effects as well. So there are multiple ways. Bayes wave is probably the preferred option right now, in my opinion.
Last question online by an anonymous attendee. What is the accuracy and inference speed needed in gravitational wave modeling nowadays and in the future?
So as our gravitational wave detectors become more and we get to higher and higher SNR, our models they're going to be probed even further, and they're going to have to be even more accurate. Now, there's a formula. I won't go into details, but you're welcome to read the paper by Emily Baird et al., which gives a relation to how accurate your model is to numerical relativity in order to distinguish it for a given SNR. So what it does, it maps the signal to noise ratio to how accurate your model is. So if your model is, for example, of accuracy, let's say 0.99999, where the accuracy range is between 0 and 1, you can map that to a signal to noise ratio, and you can see at what signal to noise ratio that signal needs to be in order to distinguish it from numerical relativity. So there is this formalization that exists, and it completely depends as to the accuracy requirements, completely depends on your gravitational wave detector. So as you'll hear in this afternoon, as we go towards LISA and those gravitational wave signals become even louder and louder and louder, our models need to be even more accurate than what they are right now. So it completely depends on which gravitational wave detector you're analyzing.
I think also on the more technical side, there's a lot of work to use GPUs to also accelerate this, especially on the LISA community now. So you should learn a bit more about that in the afternoon. Any question in the amphitheater? Yep.
Thank you very much. So I have two questions. The first one is about nested sampling. You explained very well the general idea, and I got it, but could you spend more time explaining, how it works in detail, if it's possible? And then second question, why should I use BILB instead of any other package or library? Could you elaborate a little bit more? Thank you.
Yeah, no, again, a very good question. So the reason I didn't spend too much time on it because at each point that it draws a new sample, it essentially does an MCMC walk in order to choose that next point. So what you end up doing at initial point here, you do an MCMC walk to try and find a higher likelihood region within your likelihood constrained problem. And then you keep this over and over again to try and converge to the point, try and converge to the maximum likelihood point or the highest probability region. So it is the same step over and over again. It's a very simple algorithm. It just is a process that happens over and over again. The hardest point is drawing samples from within the likelihood constrained prior. That is a very challenging thing to do because you need to be able to work out a contour of constant likelihood around your space and make sure you draw a sample from within that region. There are lots of different techniques to do this. People have used normalizing flows to do this. People have used more traditional techniques as well. I won't go into detail because it is quite complicated, so I'm more than welcome to talk about it later. Now, in terms of which sampling package to use, as you say, there are lots of different packages out there. For example, there's BILB, there's PyCBC Inference, there's Rift, rapid iterative fitting, all of these different techniques. There are all these different packages that will allow you to do gravitational wave Bayesian inference. The reason BILB is talked about here in these slides is because it is the main or the flagship software package that's used by the LIGO-Virgo-Cagra collaboration. But at the end of the day, the results you get from all of the different individual packages will give you the same results. As long as you give it the same data, you condition the data correctly, you feed in all of the settings, exactly the same, they'll all give you the same result because they all use the same underlying stochastic sampling packages that are available out there. They'll all interface with, for example, MC or Dynasty. But yeah, BILB is a flagship software package that's used by the LIGO-Virgo-Cagra collaboration.
On a more practical note, it's also the one you will use for the tutorials. So you have an introduction. Any other question? Now, just check if there is a new question online. Nope. Well, okay. Well, thank you again, Charlie.